Welcome to The Explainer. Today, we're going to tackle a concept that's woven into the very fabric of our universe. It's something that dictates the flow of time and, well, the ultimate fate of everything in it. That concept is entropy. And to really get it, we're going to start with a simple kitchen mystery.
So let's start with something you've probably wondered about. You can crack an egg, whisk it up, and scramble it into a chaotic mess. Easy. But have you ever seen anyone unscramble one? I mean, take that mess and turn it back into a perfect yolk and white? Of course not. And this isn't just about eggs. So many things in nature seem to follow a strict one-way street. And right here, this is our first big clue. On the left, you've got this beautiful, neat, predictable arrangement of molecules in a crystal. That's a state of low entropy, or low disorder. But on the right, you have a gas, with molecules just bouncing all over the place randomly. That is a state of high entropy, or high disorder. This contrast from order to disorder is the key to everything.
That slide from order into disorder? Yeah, that's not a coincidence. It's a fundamental rule of the game. From an ice cube melting into a puddle to a building slowly crumbling over centuries, the universe seems to be relentlessly marching down this one-way street, always heading towards more chaos.
And that rule, the scientific property that acts as the universe's traffic cop, forcing everything down this one-way path, well, it has a name, and it's the answer to our egg mystery. It's called entropy.
All right, so what is it officially? If we look at the textbook definition, entropy, which we represent with the letter S, is a measure of a system's molecular disorder, or randomness. You can kind of think of it as the universe's official accountant for chaos. And the name itself is pretty cool. The physicist who came up with it, Rudolf Clausius, was really deliberate. He took the Greek word trope, which means transformation, and styled it to sound like the word energy. Why? He wanted to hammer home just how fundamental and deeply connected these two concepts really are.
Okay, so if entropy is the measurement of disorder, what's the actual rule it follows? What's the law that's driving this relentless march toward chaos?
And here it is. This is the big one. It's called the increase of entropy principle, but you probably know it as the second law of thermodynamics. For any isolated system, and hey, the entire universe is the ultimate isolated system, total entropy can only go up. It can never, ever go down.
Now, think about what that really means. It's kind of staggering. Every single real-world process, from brewing your morning coffee to a star-going supernova, generates entropy. The total amount of disorder in the universe is always increasing. You simply cannot run a process that results in a net decrease in total chaos. It's impossible.
So how does that actually work in practice? Well, you have to look at two things: the system, the thing you're focused on, and its surroundings, which is, well, everything else. The total change in entropy is just the sum of the changes in both of those. And that total sum, it always has to be greater than or equal to 0.
And that leads to this really crucial point. It's almost like a loophole. You can create order in one little spot. You can build a house or freeze water into perfectly ordered ice cubes. But, and this is a huge but, doing that will always create an even greater amount of disorder somewhere else. There is no free lunch when you're trying to create order.
Your refrigerator is the perfect example. Inside the fridge, that's our system, things get colder, more orderly, so its entropy decreases, right? Let's say by 2 units. But to do that, the fridge's motor pumps heat out into your kitchen, these surroundings, making it warmer and more disorderly. This increases the kitchen's entropy by, say, 3 units. So what's the net result? Total entropy still went up by 1 unit. The law always holds.
So this isn't just some abstract bookkeeping. This principle has huge real-world consequences for something we all use every single day: energy.
Let's look at heat transfer. The more irreversible a process is, the more entropy you're going to generate. So if you transfer heat across a really big temperature difference, like you see on the right, that's super inefficient, highly irreversible, and it creates a ton of entropy. A smaller gap, though, much more efficient, and it generates far less waste.
And this brings us to a really profound insight about the quality of energy. See, work, like a spinning shaft lifting a weight, that's organized energy. All the molecules are basically moving together.
It's low entropy and super useful. Heat, on the other hand, is disorganized energy, just random molecular motion. It's high entropy and, frankly, a lot less useful.
So here's the cosmic 1-2 punch. The first law of thermodynamics tells us that you can't create or destroy energy. The quantity is always conserved. But then the second law comes along and says that with every single real process, the quality of that energy is bound to degrade, as organized work inevitably turns into disorganized heat, increasing entropy every step of the way. And, this whole idea isn't just for a physics lab. Think about it like this. An organized army is an effective, low-entropy force. 10 separate, disorganized divisions are a high-entropy mess and easily defeated. The old saying, divide and conquer, is basically just a military strategy for increase the enemy's entropy and conquer.
All right, so we get the rule. Disorder always increases. But so what? What does that mean for everything? What are the bigger consequences here?
Well, for starters, it gives us time itself. Think about it. Since the total entropy of the universe is always increasing, it provides a clear, unmistakable direction for the passage of time. The past is the state of lower entropy. The future is the state of higher entropy. You remember the past, not the future, because of entropy.
But why does time have this arrow? To see that, we have to zoom all the way down to the microscopic level. The answer lies in a number symbolized by W, which represents all the possible ways you can arrange the tiny parts of a system without changing how it looks from the outside.
And this elegant formula, the Boltzmann relation, connects that big picture property of entropy, S, to the microscopic world of probabilities, W. A scrambled egg has just an astronomically higher number of possible arrangements for its molecules than an unscrambled one. Its W is higher, and therefore so is its entropy. This is why you can't unscramble it. It's just statistically impossible.
So, let's bring all this together. What's the ultimate takeaway from this journey into disorder?
The physicist Sir Arthur Eddington said it best. Entropy isn't a property of one molecule. It's a property of the arrangement of all the parts together. It's like beauty or a melody. It arises from the whole. And the strangest part is that this feature of arrangement can be measured and calculated, just like mass or distance.
And that leaves us with a final, really big thought. If the universe is constantly moving towards a state of greater disorder, it implies it must have started in a state of near-perfect order. And what does it mean for its end? It suggests a future of maximum entropy, where all useful energy has degraded into waste heat, a quiet, disordered, and uniform cosmos. A truly sobering thought, and it's all thanks to entropy.